Mars hits you with surface radiation around 100 times higher than Earth's background, and we still plan to build a city there. In this video, we're going to stop daydreaming about glass domes and actually design that city, where you can safely put it, how you hold an atmosphere inside rock without it tearing itself apart, what streets look like when they're pressurized tunnels in 0.38 G, and how that first Martian capital quietly turns humanity into the kind of alien civilization we've been searching for around other stars. The first thing you have to understand is scale. Mars is about 3,390 kilometers in radius, around 2,100 miles, roughly half of Earth. Because the planet is smaller, the surface curves away under you faster. A city that stretches 50 kilometers across, about 31 miles, is already sitting in a noticeable shallow bowl. That matters for everything: long pipelines, high-speed trains, radio links, even how far you can see across the surface from a tower. Time hits you next. A Martian day, a sol, is 24 hours and 39 minutes. It is close to an Earth day, but not the same. If you tried to keep all your work shifts and clocks tied to Earth time, every day on Mars they would slip by 39 minutes. In a couple of weeks, your morning shift would start in the middle of the local night. So a Martian capital runs on its own time standard. Clocks, school schedules, transport timetables, all line up with sols, not Earth days. Then you look at the year. Mars takes 687 Earth days to go around the Sun. That stretches the seasons. Winter is not a few months. It can sit on your city for around 150 sols. Power demand, heating systems, how much food and fuel you store when you schedule heavy outdoor work, all of that has to survive a long, deep cold season without a rescue ship dropping in from Earth. So once you accept that your city is locked to a different clock and different seasons, you hit the next decision. Do you chase warmth near the equator, or do you move into harsher but more useful terrain away from it? Most people picture Martian cities sitting right on the equator under strong sunlight with endless flat red ground. Reality pushes you a bit away from that line. The best targets are probably in the mid-latitudes, roughly 30 to 45 degrees north or south. These belts offer two critical things at once: usable sunlight and buried water ice. Equatorial regions can actually get warm at times. In summer, at local noon, the ground temperature can climb to around 20 degrees Celsius, about 68 Fahrenheit. That sounds nice, until you remember how thin the air is. The heat leaks away fast and night can crash below minus 70 Celsius, about minus 94 Fahrenheit. You swing from cool room temperature to deep freezer in a single day, every day. Go closer to the poles and the opposite problem hits. There is a huge amount of ice locked into the ground, but winter becomes an almost sunless deep freeze. That is a nightmare for a city that depends on solar power and needs light for crops and operations. So planners look to places like Arcadia Planitia in the northern mid-latitudes. Broad flat plains, good for landing fields and surface construction. Orbital data suggests there is water ice just 1 to 2 meters under the surface, 3 to 7 feet, which is perfect for drilling and melting. Temperatures are still extreme but a bit more manageable, maybe between about minus 20 and minus 80 Celsius over a year, roughly minus 4 to minus 112 Fahrenheit. Still hostile, but slightly less insane for long-term operations. Once you have a rough latitude band, another question hits you. Do you put your capital high for the view and sunlight, or low for survival pressure? Because on Mars, elevation is not just scenery, it is life support. Earth's mountains thin the air gradually. On Mars, with almost no air to begin with, small changes in height produce big changes in pressure. Average surface pressure is around 600 pascals. Earth's sea level is about 101,300 pascals, so you are dealing with less than 1% of Earth's air from the start. And even that small amount can double or halve over a few kilometers of height. If you place your city in a deep basin like Hellas Planitia, one of the lowest spots on Mars, you can gain maybe 30 to 40% more atmospheric pressure than the planet's average. It is still nowhere near breathable. You will always need suits outside, but that extra thin blanket helps. It gives you a bit more protection from radiation, a small boost in how well the air holds heat, and a little more margin before a leak in your structures faces hard vacuum. If you climb onto high plateaus or tall volcanic flanks, that already thin air drops even further. You end up in conditions where the outside pressure is so low that any failure in your habitat walls pushes you straight toward explosive decompression territory. So for a first capital, the safer choice is boring, low and flat, not dramatic cliffs and vistas. You might think that once you choose latitude and height, the problem is done, but now the planet's weather steps in, and even though the air is thin, its dust and storms can still cripple a young city. So how do you build in a place that can sometimes almost turn off the sun? Martian winds in normal conditions run around 5 to 20 meters per second, 11 to 45 miles per hour. In stronger storms, gusts can push 50 meters per second or more, about 110 miles per hour. That sounds like hurricane force, but because the air is so thin, the actual force on a wall feels weaker than a light breeze on Earth. Your buildings are not going to blow over from wind pressure alone. The threat comes from dust. The particles are tiny, often less than 10 micrometers across, more like smoke than sand. They get lifted high into the atmosphere and spread around the planet. They cling to surfaces using static charge, and they get into every gap and hinge they can reach. For a city that uses solar panels, radiators, cameras, and moving machinery, that is a constant hazard. Every 3 to 6 Martian years, the planet can spin up global dust storms. During these events, sunlight at the surface can drop by 80 to 90% for days or weeks. That is enough to starve solar grids, cool the surface even further, and coat hardware with thick, sticky dust. So when you pick a site, you check orbital maps for where storms usually start. You favour regions where local topography breaks up wind patterns and tends to trap dust instead of launching it. Your capital needs a location that is at least slightly less likely to be the engine of those global storms. Even with a good site, the open surface is still brutal, thin air, harsh radiation, big temperature swings, and endless dust. That raises the next hard question. If the surface is that bad, why not hide the city inside the planet wherever you can, and let Mars itself be part of the shielding? Orbital imagery has shown chains of deep pits and collapsed roofs that probably mark ancient lava tubes, huge tunnels carved when lava once flowed through solid rock. Some of these tubes could be tens of meters tall and hundreds of meters wide, big enough to fit city blocks. Craters offer similar advantage, with high walls and thick rims of rock around a lower, flatter floor. Rock and soil, what we call regolith, are excellent shields. Just 2 to 3 meters of regolith piled on top of a habitat around 6 to 10 feet can cut dangerous cosmic radiation down to levels closer to what you get at Earth's surface. Instead of hauling millions of tons of shielding from Earth, you dig into a crater wall or inflate habitats inside a lava tube and let the overlying rock do the work. That means the first Martian capital probably will not look bright and open from a distance. The real city will be a network of pressurized tunnels, chambers, and halls cut into rock or covered with regolith. Only the landing pads, mining systems, power fields, and heavy industry will sit fully exposed. Life, housing, parks, hospitals, schools, all of that will sit under a roof of Martian stone. And that sets up the next, even tougher problem. Once you have picked this hidden, shielded site for your capital, you still have to hold a full Earth-style atmosphere inside thin walls, while the outside sits just above vacuum. So how do you build air, pressure, and breathing into a whole city without turning it into a bomb waiting to burst? Step outside on Mars without a suit and you don't explode, but you also don't stay alive for long. So how do you build indoor air that behaves like a small planet, not a thin balloon waiting to burst? On Earth, at sea level, you're used to about 101 kilopascals of air pressure. That's your normal. That's what your lungs, your blood, your eyes are built for. On Mars, the outside pressure is only around 600 pascals. That's less than 1% of what you're breathing right now, and it's even below something called the Armstrong limit, around 6,300 pascals, where the liquid parts of your body, like saliva and tears, can start to boil without any heat just from low pressure. Mars sits well under that line. So your Martian city is not a town with bad air. It's a cluster of hard shells holding full, artificial atmospheres inside a near vacuum. Inside, maybe 50 to 100 kilopascals. Outside, almost nothing. That difference is brutal. Every square metre of wall or roof about the size of a small dining table has to hold back the force equal to several tons on Earth. 5 to 10 tons per square metre is a good ballpark. Spread that over a big roof and your nice open plaza is quietly trying to rip itself apart 24/7. That's why Martian architecture is closer to building a fleet of submarines than streets of regular houses. Every room, every corridor is part of a pressure vessel. The question is, do you really have to copy Earth's exact pressure inside, or can you cheat a bit and still keep people alive and comfortable? You actually don't need full Earth sea level pressure in your city, so why not lower it, cut the stress on your walls, and still give everyone safe air to breathe? Most human physiology cares more about how much oxygen you get than about the total pressure number, as long as you don't go too low. Many habitat designs on paper today use something like 50 to 70 kilopascals inside, roughly half to 2/3 of Earth sea level. They then bump up the oxygen fraction. Instead of 21% like on Earth, you might run 30 to 40% oxygen, with the rest as safe, inert gases like nitrogen and argon. That way, the partial pressure of oxygen, the slice of the total that is actually oxygen, stays high enough for normal breathing, but the overall push on your hull drops. Less total pressure means less force trying to blow your roof off. Take a simple example. Picture a roof about 100 square meters in area, roughly a small basketball court. At around 60 kilopascals inside with almost vacuum outside, the total outward force on that roof is on the order of a few million newtons. In everyday terms, think of holding back the weight of about 600,000 kilograms on Earth, roughly 1.3 million pounds, all the time. With no brakes. That is what your bolts, welds and support beams are dealing with. So the city's design language becomes a catalogue of pressure vessels. Every change in pressure, every step from one environment to another, is a risk. That leads to another choice that kills a lot of science fiction art, if you're serious about surviving for decades. Do you really cover your city in giant glass domes? Or do you pick shapes that are far less pretty and far more forgiving when something goes wrong? Domes look amazing in concept images, but engineers prefer cylinders, tunnels and buried shells because those shapes handle pressure more evenly, and Mars gives you free rock to help. A nice underground horizontal cylinder, 4 to 10 meters across, about 13 to 33 feet, surrounded by 2 to 3 meters of regolith, 6 to 10 feet, spreads the load around its whole curve. The soil itself helps carry the stress. Instead of one huge fragile bubble, your city becomes a honeycomb. Parallel tubes for housing, labs and streets stacked in layers, cross-connected like a subway system that people live in, instead of just travel through. A few transparent domes might exist for parks or public squares, but they'll be small, heavily reinforced and probably still partly buried or backed by secondary shells. Most of your daily life happens in thick-walled tunnels, not under a thin window to the sky. But filling all those tubes and halls with air raises the next issue. Mars gives you almost no breathable gas to start with. It's basically a carbon dioxide planet. So where does the oxygen, the nitrogen, the normal air for this city actually come from? Mars does at least hand you one big resource, a sky made of carbon dioxide. About 95% of the Martian atmosphere is CO2. Your city uses that as raw material. You run compressors that pull in the thin outside air and squeeze it up to useful pressures. You chill it and separate out the CO2 from the trace gases like nitrogen and argon. Then you bring in water from melted ice in the ground. Electrolyzer units split that water into hydrogen and oxygen. Now you have two key ingredients: hydrogen from water, carbon dioxide from the air. Sabatier reactors, a type of chemical plant, combine hydrogen with CO2 to make methane and more water. The methane is a good rocket fuel and a good energy storage gas. The extra water goes back into your loop. The oxygen from electrolysis becomes the breathable part of your city's air mix. The nitrogen and argon, which show up in small amounts in the Martian atmosphere, are captured and used as filler gas, the safe background component that bulks out your indoor atmosphere. Over time, the system tightens. A mature city might recycle more than 95% of its air. Exhaled CO2 from people, waste gases from factories, leaks picked up by scrubbers, all go back into processing units. Only a small fraction of gas mass is lost per year, through tiny leaks and unavoidable venting. That loss is topped up by pulling more CO2 from the outside air and more water from local ice. Still, with all this machinery, all this pressure and gas flow, there is an uncomfortable question behind every door. What really happens when something cracks, when a seal fails, when an airlock jams halfway? How do you stop one local failure from turning into a chain reaction that rips through the whole city? On Mars, every entrance is a pressure staircase. Outside, you're at about 600 pascals. A suit might run at a few thousand pascals. Habitats run at tens of thousands. You never want a direct, wide-open path from full city pressure straight to the vacuum outside, so airlocks are built in stages. A rover dock, then an intermediate pressure chamber, then the full pressure corridor. Despite what movies show, most real-world leaks are slow. On space stations, actual measured leaks are often just tens of grams of air per day. A tiny flow you only notice with sensitive instruments. That's the model you want for your Martian city. Small leaks, detected early, fixed before they get worse. To do that, the city runs constant monitoring. Pressure sensors in every segment, acoustic detectors listening for the faint hiss of escaping gas, flow meters on main lines. Software watches the numbers all the time, and when something drifts, alarms fire fast. The whole urban layout is built with compartmentalization in mind. Residential blocks, industrial modules, transit tunnels, all are divided by bulkhead doors that can slam shut in seconds. If a hull panel in one industrial bay cracks, you don't let the whole district equalize with the outside. That bay isolates, the next ring of corridors seals, and life support in the rest of the city barely notices. This turns city planning into risk mapping. You decide where you can safely shut things off, where you must keep routes open, who gets priority air and power in a serious breach. Your map of neighborhoods doubles as a fault tree diagram. Every mistake in that map is a path where a single damaged wall could kill thousands. And all of this, the pressure, the shells, the monitoring, sits on one more alien twist. Your body itself has to live long-term in Martian gravity, at about 0.38 g. So what does that do to how you build floors, towers, and even sports fields inside this pressurized, buried world? Low gravity sounds like a cheat code, but on Mars it quietly rewrites how your body works. Now every building in the city has to be shaped around that new normal. First, you need to know what 0.38 g actually feels like in your own legs. On Earth, gravity pulls at about 9.8 meters per second squared. Mars pulls at about 3.71, roughly 38% of that. If you have a mass of 80 kilograms on Earth, about 176 pounds, your weight on Mars drops to something that feels like 30 kilograms, around 66 pounds. Your joints carry far less load, your steps feel lighter, stairs feel more like a short ramp than a workout. You can carry heavy equipment that would be painful on Earth, and you can jump higher without straining. That sounds great, until you remember what happens to astronauts in 0G. On the space station, even with exercise, they can lose around 1 to 2% of their bone mass per month, and muscles thin out because they are not working as hard. Mars is not 0G, but it is still a big drop. Day after day, your skeleton and your heart do not get the same stress they evolved for. Over years, especially for people born and raised on Mars, bones could grow lighter, muscles could adapt to do less, and a trip to Earth at full 1G could feel like suddenly wearing a concrete suit. You might need medical support just to stand upright in Earth gravity, so low gravity gives you easier movement but at a long-term health cost. That leads straight into the next design problem. If weight is cheaper in this environment, how far do you push your buildings upward before low gravity stops being an advantage and starts being a risk? Lower gravity means that the force pushing down on foundations is much smaller. Concrete, steel and bricks made from Martian regolith all carry lighter loads. So in theory, a 20-story building in 0.38 GG stresses the ground like a 7 or 8-story building back on Earth. That tempts you to stack towers everywhere. Less structural material, more height for the same base, and plenty of room inside the rock cover. But you are not in open air. Every extra metre of height inside a pressurized building increases the pressure difference across the walls and adds more potential energy if something fails. A fall from 10 stories in low gravity might hit the floor slower, but if that fall punches into a pressure window or cracks a wall, you have a life support emergency, not just a broken leg. Evacuation and firefighting are also more complex in tall sealed towers, so the city does not go for megatall skyscrapers at the start. It spreads sideways first. You get wide, multi-deck tunnels carved into rock stacked 2 or 3 levels, with terraced caverns where floors step up the crater wall. Then once the pressure systems and emergency procedures are mature, you add mid-rise light towers, maybe 10 to 20 stories, tied directly into the surrounding rock and shield layers. The real limit is not the strength of concrete, it is how much vertical risk your life support system can safely handle. With that sideways multi-level layout set, movement inside the city changes too. In 0.38 GG, your daily commute, and even your cargo logistics, stop behaving like the FUVs do on Earth. So how do you redesign transit when climbing a flight of stairs barely feels like effort? Low gravity plus indoor controlled air makes human power a lot more effective. Walking upstairs costs less energy, so you can use vertical space more aggressively. Overhead walkways, multiple floor connections, and bridges between tunnels actually get used, instead of people avoiding them out of laziness. Bicycles become extremely efficient. At 0.38 G, with comfortable air and no strong headwinds, a normal person can cruise at around 40 km per hour, about 25 miles per hour for short trips, turning bike lanes into a serious transport option inside main corridors. For freight and longer distances inside and between districts, you use rail and maglev. Trains on Mars haul lighter effective weights, so wheels and tracks see less wear. Maglev capsules in low-pressure or vacuum tunnels under the city can move at high speed with little friction. Elevators also get cheaper to run. Lifting a 1,000-kilogram payload, about 2,200 pounds of mass, feels like lifting only 380 kilograms of weight because of the lower gravity. Motors are smaller, cables are under less tension, safety margins are easier to meet. All that lighter motion opens up more room for recreation, but the second you let people play in low gravity, the physics of injuries and disasters changes too. So how do you design sports and parks in a world where a casual jump can put your head near the ceiling? In 1G, a trained person might jump 1.5 to 2 meters high, around 5 to 6.5 feet. In 0.38 G, the same leg power can easily launch you into the air 4 to 5 meters, 13 to 16 feet. You stay airborne longer, your path is slower, and what feels like a gentle hop can carry you right up to a ceiling or pressure window. Impacts on landing are weaker because the weight is lower, but the distances and contact points are different. That changes safety rules. Large play areas and sports zones cannot have unprotected, transparent walls that separate you from vacuum. Any window or thin hull section near recreation has to be double-walled, with a backup layer behind it. You pad those zones with foam, curved corners, and no sharp projections pointing toward the outer shell. Helmets and padding become standard for many active sports, not just for head protection, but to reduce the chance that a collision sends someone into a critical panel. The city has to accept that low gravity invites people to push their bodies, and then design those spaces so that a bad landing does not become a structural emergency. But even with careful design, you still have that long-term medical question hanging over you. If 38% of Earth gravity is not enough to keep hearts and bones healthy for a lifetime, what backup does the city need to build straight into its walls? Here is where the plan gets strange. To live on a low-gravity planet, you probably still need pockets of almost Earth gravity inside the city. Data from astronauts in 0G show serious strain on the heart, blood vessels, muscles, and bones. We do not yet know the exact lower limit where gravity is good enough long-term, but 0.38 G might be too low, especially for multiple generations. So the city hedges its bets with rotating sections built like giant wheels. These are centrifuge rings that spin at a few rotations per minute. When you stand or run on the outer rim, the outward push from rotation acts like extra gravity. With the right radius and spin rate, you can get total effective gravity close to 1 g, similar to Earth, or at least up to 0.8 g. For example, a ring about 50 meters in diameter, roughly 164 feet spinning at around 3 rotations per minute, can give you nearly Earth-like pull at the floor. You could put a gym there, medical rehab areas, maybe even some living quarters for people who need more time at higher gravity. From the inside, the floor curves upward around you, and if you look across the ring, you see other people standing sideways relative to you, held down by the spin. These spinning habitats cost a lot in engineering effort, but they are an insurance policy. They give doctors a way to counter bone loss and muscle shrinkage. They let kids who will someday visit Earth train their bodies for full 1 g before they ever step into a rocket. And they add one more layer of complexity to the city's shape, static tunnels dug into rock plus rotating rings hidden in its core. But even if you handle gravity, motion and long-term health, there is a threat you cannot feel with your muscles at all. Something that passes straight through your skin, your walls and even parts of the rock above you. So how does invisible radiation end up deciding which floors you sleep on, and how deep your entire Martian city has to bury itself to survive? You can't see it, you can't feel it, but on Mars it quietly decides where you're allowed to live, so how bad is the radiation actually? On Earth, you sit under a thick atmosphere and a strong magnetic field. Together, they cut most of the dangerous particles from space down to a gentle background of maybe 2 to 3 millisieverts of dose per year on average. That's your normal, you don't think about it. Mars does not give you that protection. No global magnetic field, and only about 600 pascals of air above you. That thin layer barely slows down the high-energy particles coming from the sun and from deep space. The Curiosity rover carried a radiation detector, and the numbers it reported on the surface were around 230 millisieverts per Earth year. That's roughly 75 times typical background on Earth, and it is close to, or even above, some career limits that space agencies use for astronauts over a whole job lifetime. So if you just walk around on the open surface, even in a suit, the clock is running fast. A few months is fine, years start to add up, decades are a real health problem. That single number forces you to change your floor plans. Bedrooms, schools, hospitals, they cannot sit right under a thin roof with the sky above. The city core has to be a low radiation zone by design, not by luck. That leads straight to the next step, because Mars is not going to hand you a magnetic field. You have to build a fake atmosphere out of rock, so how thick does that shield really need to be before living there starts to look like long-term survival, not a slow medical experiment? Radiation from deep space, the galactic cosmic rays, is hard to block. You don't stop it with a few millimeters of metal. You need mass, lots of it. A useful rule of thumb is that a layer of material with 5 to 10 grams per square centimeter of thickness already knocks down a big chunk of the incoming particles. Martian regolith, the loose rock and soil, has a density of around 1.5 to 2 grams per cubic centimeter. If you pile about 3 meters of this material on top of a habitat, around 10 feet, you end up with something like 450 to 600 grams per square centimeter of shielding. That is way beyond the minimum. It doesn't give you zero radiation, but it can cut the dose by an order of magnitude or more. Suddenly that 230 millisieverts per year number can drop into a band like 5 to 20 millisieverts per year inside your main living spaces, which is much closer to high-altitude life on Earth, and more realistic for decades of residency. This is why almost every serious design for Mars does the same thing. It buries people, tunnels dug into rock, habitats covered with thick regolith, bases pressed into crater walls or canyon sides. For the first few decades, your biggest machines are not skyscraper cranes. They are boring machines and regolith movers. You spend more on digging than on building tall. But there is a trade-off here. Hiding under 3 meters of soil cuts your connection to the outside world. People still need to see the sky sometimes, so how do you let light and views in without throwing away all that hard-won shielding? You solve it by making a few dedicated, heavily controlled sunrooms instead of whole transparent districts. These are compact spaces, carved into rock but opening toward the surface through thick, multi-layer windows. The clear panels might be several centimetres thick, an inch or more, made from tough glass or transparent ceramic like aluminum oxynitride, with extra layers of plastic rich in hydrogen that helps block some radiation. These rooms are not for living in all day. The city accepts that time spent there adds a small extra dose per year, maybe 1 or 2 millisieverts on top of the baseline. In return, you get real sunlight, real shadows, and a true view of the horizon and the sky. To keep that risk under control, the city tracks access. Your time in these high-view zones is logged, a bit like how divers track their time underwater. Stay within limits, you are fine. Ignore them and medical staff will have a problem on their hands 10 or 20 years down the line. Even with deep burial and controlled sunrooms, the radiation from space is still coming in from all directions. So the next question is simple. If particles will hit anything in their path, why not let your least fragile systems take the hit first and use them as shields for the people inside? Radiation does not care whether it passes through a rock, a water tank or a warehouse, so you arrange your city like an onion. The outermost layers hold things that can handle more exposure and that also happen to be good shields. Massive water tanks for storage and processing, fuel depots holding methane and oxygen, greenhouses full of water-rich plants, soil and nutrient solutions, industrial warehouses and heavy equipment yards. A metre-thick wall of water about 3 feet is excellent shielding because hydrogen atoms are very effective at slowing down charged particles. Large tanks placed on the side of the city that faces the average incoming cosmic ray direction or the daytime sun can soak up a lot of the radiation before it ever sees your living quarters. The same goes for stacks of cargo, propellant tanks and dense machinery. Deeper in behind this industrial skin, you place the residential districts, schools, offices and hospitals. Those inner zones sit in a partial radiation shadow surrounded on all sides by bulk mass that takes the first punch. Overhead, they still have the 3 meters of regolith. Sideways, they have tanks, warehouses and farm modules. You turn your own infrastructure into armor. But there is one more spike you have to design for, not the steady drizzle of galactic rays, but sudden bursts from the sun itself. A big solar flare can hammer Mars with particles for hours or days. So when that happens, where does everyone go? And how does the city make sure that go now actually works? Solar particle events are short, sharp and intense. Unlike the slow background, they can deliver dangerous doses over a very short time. The good news is that you usually get some warning. Satellites in Mars orbit and instruments watching the sun can see a flare and the outgoing particle storm, giving you tens of minutes to a few hours of lead time. When those alarms trigger, the city switches into storm mode. Everyone moves to dedicated shelters, usually the deepest, best shielded parts of the settlement. These cores sit under more than 3 meters of regolith, sometimes 5 or more wrapped in thick water tanks and other hydrogen-rich materials, maybe with inner linings of plastics designed specifically to block high-energy protons. These spaces are not small bunkers for a handful of people. They are big enough to hold entire neighborhoods, with seating, air, water, toilets and communications. Think of them as the basement level of the city, already in daily use for storage, data centers or transit, but ready to switch to emergency shelter mode at any time. During a major event, people might stay there for many hours, even a day or two, until radiation levels outside are dropped back to the usual background. Life slows down, but it does not stop. Once the storm passes, everyone climbs back up to regular levels and the system resets, ready for the next hit. So between constant background rays, rare but violent solar storms, and the need for heavy shielding from floor to ceiling, radiation ends up acting like a hidden zoning law for your whole Martian capital. Bedrooms go deep, parks get thick roofs, industry wraps around housing like armor, and after you have dug all that rock, filled all those tanks and stacked all those shields, you still face one more basic problem. Even if people are safe underground, the machines that keep them alive need power. A lot of it, and on a planet that is colder, darker and dustier than Earth. So how do you build an energy system that does not die the first time Mars decides to dim the sun for weeks? You already buried the city to survive radiation, but that rock cover does nothing if the lights go out. So how much power does a serious Martian city actually need, and can the sun alone deliver it? At Earth's distance from the sun, the energy hitting 1 square metre at the top of the atmosphere is around 1,360 watts. Mars is farther out, about 1.5 times Earth's distance. That drops the sunlight on each square metre down to roughly 590 watts at the top of the atmosphere. By the time it passes through Mars' thin, dusty air and hits your solar panels and you factor in real panel efficiency, maybe 20 to 30%, a square metre of solar array might give you around 100 to 150 watts in clear conditions. Now scale up. A city of 100,000 people is not a campsite. It is more like a small Earth city. Life support, lighting, heating, cooling, pumps, mining, industry, computers, transport. It is easy to hit a continuous demand of 100 to 300 megawatts of electrical power, and that does not even include big industrial expansions or a busy spaceport. To get that level of power from solar alone, you're talking about hundreds of thousands of square meters of panels, easily several square kilometers, plus all the support structures, cabling and cleaning systems, and those panels sit in a place where dust is everywhere. Even in normal weather, performance slowly drops as fine particles settle on the glass. So you need robots, brushes, blowers, maybe electrostatic cleaners constantly working just to keep your main power source from fading day by day. Every kilowatt becomes a maintenance job, and then Mars reminds you that its sunlight is not stable. Dust storms can dim the sky by 80 to 90%. The Opportunity rover died in 2018 when a global storm cut its solar input so low for so long that its batteries never woke back up. Your city cannot be allowed to follow that path, so how do you build a grid that stays alive when Mars decides to turn the dimmer almost all the way down for weeks? The answer is that you use solar hard when you have it, but you never trust it alone. You overbuild the solar field so that on a clear day you produce much more than you immediately need. The extra power charges batteries, spins up flywheels, heats up thermal storage tanks, and creates chemical fuels. You also design explicit storage targets. For example, you might size your batteries, flywheels, and fuel reserves to keep the city running at full load for 2 to 3 days without any sunlight at all. For local storms that only last hours or a couple of days, that buffer carries you through. Once the sky clears a bit, your oversized solar fields start refilling the reserves, but that still leaves global scale events and long dim seasons. For those you need something that does not care if there is dust in the sky, something that runs day and night, week after week. So what becomes the real heartbeat when solar is only the surface layer? That role almost certainly falls to nuclear reactors. We already have designs on paper and in tests. Kilowatt-class fission reactors, such as NASA's kilopower concept, can produce around 10 kilowatts of electric power from a compact unit weighing on the order of 1.5 tons. That is good for outposts and early bases. For a city, you scale that idea up. A handful of megawatt-class reactors, buried under regolith berms for shielding and safety, can deliver stable tens of megawatts into the grid. Modern small modular reactors on Earth target outputs between 50 and 300 megawatts. A Martian capital could realistically install something like a 50 megawatt fission plant within its first decade, once heavy equipment and fuel supply chains are established. You do not park this plant next to housing. You put it in a crater or deep trench several kilometers from residential zones. Heavy shielding comes from both engineered materials and the surrounding rock. Heat exchangers carry waste heat into water loops that melt subsurface ice and feed district heating systems. The reactors run at a steady, predictable output, forming the base of the city's energy stack. Solar then rides on top of that, reducing fuel burn when the sun is kind, backing off when you need to conserve nuclear fuel. Even with reactors, you still need storage. Mars has conditions that actually make some storage methods better than on Earth. So once you have basic batteries, what else do you add to stabilize the grid in thin air and low gravity? Standard battery banks still do a lot of work. They respond fast to demand changes, they smooth out short dips in solar output, and they cover quick transitions when reactors shift output or lines trip. But they are heavy, need rare materials, and do not scale infinitely. So you add other tools. Low air density and weaker gravity are perfect for tall, high-speed flywheels. Put a rotor in a vacuum housing, spin it up with surplus electricity, and it stores energy as rotation. When you need power back, you let it drive a generator. With less gravity pulling on the bearings and almost no air drag, these systems can be more efficient and longer-lived than on Earth. Then there is thermal storage. You can dig pits into the regolith and drop in insulated tanks filled with molten salts or other heat storage fluids. During the day, or when reactors run beyond immediate demand, you dump extra heat into these salts, raising them to temperatures of 500 to 600 degrees Celsius, 930 to over 1,100 degrees Fahrenheit. At night or during storms, that stored heat runs steam turbines or other heat engines to regenerate electricity. On top of that, you use chemical storage. When you have surplus solar output, you run electrolysis on water to split it into hydrogen and oxygen. The hydrogen can be stored alone or reacted with carbon dioxide from the Martian air in Sabatier reactors to make methane. These gases sit in high-pressure tanks or underground caverns. Later, during low power periods, they feed fuel cells or combustion generators to deliver electricity back to the grid. The same methane and oxygen also supply your rockets, giving you a tight link between energy storage and transportation fuel. So with solar, reactors, and multiple storage layers, the city can keep its electronics and pumps running. But there is another piece you have to handle correctly, because on Mars, the problem is not just getting rid of waste heat, it is also about not wasting it. So how do you turn every watt of extra warmth into part of the city's climate control system? Mars is cold. Average surface temperature sits around minus 63 degrees Celsius, about minus 81 Fahrenheit. In that environment, waste heat is not a nuisance, it is a resource. A power system delivering 100 megawatts of electricity will also dump roughly that much heat into its surroundings. Instead of throwing that away into space, you route it. Pipes carrying warm coolant run under main corridors and streets to stop ice from forming where you need smooth surfaces. Heat loops snake through greenhouses to hold crops at 20 to 25 degrees Celsius, 68 to 77 Fahrenheit, without extra electrical heating. Industrial areas that must operate above freezing get priority on these loops. The city ends up with zones at different temperatures set deliberately. Core residential areas might stay around 20 to 22 degrees Celsius. Industrial sections run hotter because of machinery and heat recovery. Storage caverns and some tunnels may sit cooler to reduce energy use. Instead of an atmosphere and oceans moving heat around, pumps, exchangers and radiators do the job. Outside, large radiators still have to glow away the final excess into the thin Martian air and into space, but inside the shielded rock, most of that energy gets at least one useful job before it is dumped. Once you have that much controlled power and temperature, you are finally ready to treat water and air as closed resources, not things you burn through, which raises the next hard question. On a dry, thin air world, how do you build water and oxygen loops tight enough that a city of 100,000 people can run for years without constant resupply from Earth? Every person in your Martian city is basically walking around with part of a hidden lake on their back. So how big does that lake have to be before the city is actually stable? On Earth, a typical city dweller can chew through 100 to 300 litres of water per day, around 26 to 79 gallons. Drinking, showering, toilets, washing clothes, leaking pipes, everything. On Mars, that kind of use would kill the colony fast. So the city slams water use down hard. With aggressive recycling, at least as good as the International Space Station, you can aim for maybe 20 to 50 litres per person per day, roughly 5 to 13 gallons. That covers drinking, strict showers, cooking, and carefully designed low-flow systems for everything else. On top of that, you push recovery efficiency above 90 to 95%. Almost every drop that leaves a tap has to come back into the loop in some cleaner form, even then run the number. At those tight rates, a city of 100,000 people still has around 2 to 5 million litres of water, 500,000 to 1.3 million gallons moving through its systems at any moment. That is the equivalent of a small lake, but locked inside pipes, tanks, filters, and human bodies. You do not have giant open reservoirs, you have a continuous closed circuit. Cut that moving volume too low and there is no buffer for breakdowns, no margin when a recycler goes offline, no reserve for firefighting or medical use. So the hidden lake has to be big, and it has to be constantly topped up from somewhere local because hauling it from Earth is insane. Which leads to the next step. If you can't afford to ship lakes across space, where do you steal that first water supply on Mars itself? Mars might look dry, but the numbers say otherwise, especially in the mid-latitudes you already picked for the city. Orbital neutron instruments have mapped huge regions where just 1 to 2 meters below the surface, 3 to 7 feet, there is ice mixed into the regolith. In some places, it might be almost pure ice slabs under a thin dust cover. Your city drops drilling rigs onto the best of these deposits. Some rigs use heated probes that melt the ice and pump the liquid up. Others use heaters to make the ice turn straight into vapor, then capture and recondense it. A small test-scale system pulling 10 kilowatts of electric power might give you tens of litres of water per hour. That's fine for a base, but a city needs far more, so you scale up into megawatt-class ice mines. Multiple wells, heavy pumps, continuous operation. At that level, you can produce tens of cubic meters of water per day from each site, tens of thousands of litres, enough to cover drinking, hygiene, industrial processes, and a serious chunk of rocket propellant production. The ice fields around the city become strategic assets, like rivers and aquifers back on Earth, only this time they are frozen and buried. But all that raw ice is only half the battle. Once it turns into liquid inside your walls, almost every atom of it has to be used again and again. So how do you run a recycling chain tight enough that sweat, breath, and toilet flushes all come back as clean drinking water without choking the city in its own waste? Space stations already show the baseline. On the ISS, water processors can recover around 90 to 93% of humidity, urine, and grey water. For a Martian capital, you aim higher, into the 98 to 99% range, because you want every litre to cycle hundreds of times before you ever need to replace it. The hardware looks like layers. First, air handling systems pull moisture out of breath and sweat using condenser panels that cool the air and make water vapour condense into liquid. Showers, sinks, and washing machines drain into grey water tanks. Toilets feed into separate treatment units. From there, filters, biological reactors, membranes, and distillation units strip out solids, salts, and contaminants. Reverse osmosis and multi-stage distillation polish what is left until it hits strict drinking standards. Sensors track humidity in every major volume. If a corridor suddenly shows more water in the air than expected, it might be a leak or an equipment problem. Leaks themselves are tracked in grams per person per day. If your total city water mass starts trending down by a few hundred kilograms over a month, alarms go off, investigation teams get dispatched. In this environment, lost water is not a bill problem, it is a survival problem. Water is half of life support, the other half is air, especially oxygen. People need to breathe, plants need to grow, and anything that breaks that loop moves fast. So how do you turn a carbon dioxide sky and a closed habitat into a stable oxygen factory that can serve 100,000 lungs without pause? The good news is that each person does not actually use that much oxygen by mass. A typical adult might consume around 0.84 kilograms of oxygen per day. For 100,000 people, that is about 84,000 kilograms per month. A closed system can recycle a large fraction of that through plant photosynthesis and chemical process, but you still want robust hardware in the loop. Mars's atmosphere is about 95% carbon dioxide, and you already have compressors pulling it in for other reasons. Inside the city, you run oxygen production plants that take CO2 and split it. The principle was proven in small scale by the MOXIE experiment on the Perseverance rover, which produced grams of oxygen per hour from Martian air. For a city, you scale that up massively. Racks of solid oxide electrolysis units, drawing tens or hundreds of kilowatts steadily converts CO2 into oxygen and carbon monoxide or other byproducts. At the same time, indoor atmospheres need to stay within narrow CO2 ranges. If carbon dioxide levels creep much above 1,000 parts per million, people get headaches and their thinking gets worse. So you install scrubbers everywhere. These use materials like amine compounds or zeolite beds that chemically grab CO2 from the air. Once saturated, they are heated or evacuated to release pure CO2 back into processing lines. Plants in greenhouses also eat a large share of the CO2 and return oxygen, but you do not trust biology alone. You layer hardware on a top for stability. All this gas moves in a closed loop, but nothing man-made is perfectly tight. Air and water will find any weakness in seals or panels. Over 10 or 20 years, that tiny loss can add up to tons. So how do you keep track of every kilogram that escapes? And how low does that leak rate have to be before the city stops living on the edge? Engineers talk about leak budgets. For a big sealed system like a Martian city, you treat total air and water mass as critical inventory. Every year, you measure how much new gas and water you had to add to keep pressures and tank levels at target. That number in kilograms per year is your loss rate. If your city leaks 1% of its total air mass per year, that is a crisis. At that rate, in a decade, you have to replace 10% of your entire atmosphere, a huge burden on your production plants and water splitting systems. You want something like 0.1% per year or less. At that level, over 10 years, you lose only around 1% of your atmosphere, a level your hardware can easily replace from outside CO2 and mined ice. To hit those numbers, maintenance becomes relentless. Door and hatch seals are on replacement schedules. Pressure hulls get scanned with ultrasound or other non-destructive tools to catch micro cracks. Drones or crawling robots patrol tunnels, looking for tiny pressure drops around welds and joints. Every airlock cycle is logged. Venting events for repairs are tightly controlled and minimized. In effect, the whole city runs like a giant spacecraft that never lands, even though it is sitting on a planet. Life support is not a room in a building, it is the entire urban system. And once that system can handle 100,000 people without leaking them, or their air into the dust, the next challenge comes into focus. Feeding all of them without endless cargo ships from Earth, using only rusty rock, thin sunlight, and whatever biology you can bend to your will inside those tunnels. You can't just drop seeds in Martian dirt and call it a farm, so what exactly are you eating in a city built on rust? Start with the ground itself. Martian regolith is not soil in the way you know it. It's mainly crushed basalt rock mixed with fine dust, perchlorated salts, and some trace nutrients like iron, magnesium, and a bit of nitrogen and phosphorus. Those perchlorates are the big problem. Viking landers and later missions found them at around 0.5% to 1% in many places. They are strong oxidizers, useful for some chemistry, but toxic for humans, especially for thyroid function. So no, you do not just plant potatoes straight into Martian dirt. Step 1 is cleaning. You take regolith into processing units and leach it with repeated water washes, flushing perchlorates out into separate tanks. In some setups, you also heat it and pass it over catalysts to chemically break those salts down into safer compounds. The water itself then goes through filtration and treatment before it returns to your life support loop. Once the regolith is stripped of the worst chemistry, you still don't have real soil. It has practically zero organic matter. So you start blending it with compost made from plant waste, treated human waste, and food scraps. Bit by bit, that mix begins to behave like soil. Better structure, better water retention, more active microbes. Over the years, that homemade soil improves. At first, it lives in sealed trays and beds. Later, it becomes a more natural medium in larger greenhouses. But even perfect soil doesn't fix the next bottleneck, because Mars hits your crops with weak sunlight under dirty glass. So how do you make enough light for food when the star over your head is only giving you 43% of what you're used to on Earth? At Mars's distance from the Sun, the raw sunlight intensity is about 43% of Earth's. So if a crop on Earth likes, say, 400 watts per square meter of light at peak, Mars might only give you around 170 watts per square meter at noon, even before you put anything between the plants and the sky. Now add greenhouse structure, dust on the roof, and the fact that your transparent panels never transmit 100% of incoming light. You might end up with only 50 to 70% of that reaching the leaves. That pushes you into the range where a lot of crops will grow, but slowly, and your yields fall off. So you replace missing sunlight with LEDs. You hang dense arrays over hydroponic racks, tuned to the wavelengths plants use most, mainly in the blue around 450 nanometers and in the red around 660 nanometers. This cuts wasted energy and drives photosynthesis harder. But it is not cheap in power terms. Growing just 1 kilogram of wheat or similar crops in a tightly controlled high-yield system can cost around 200 to 250 kilowatt hours of light energy. That directly ties your food to your power grid. When the grid is strong, you're well fed. When energy is tight, you scale back high-energy crops, slow growth, or shift to plants that give more calories per kilowatt hour. Food security becomes an energy management problem. Even with perfect lighting, you still have the brutal math of calories and land. So how much growing area does the city of 100,000 people actually need? And where do you fit it when the surface is lethal and your ceiling is solid rock? On Earth, intensive greenhouse farms can hit 50 to 100 kilograms of vegetables per square meter per year under ideal conditions. On Mars, with strict control, slightly weaker light and more complexity, a safe assumption might be around 40 kilograms per square meter per year for a mix of crops in advanced systems. Say you plan for about 2 kilograms of food per person per day on average, including fresh plants, grains, fats and protein. That comes to roughly 730 kilograms per person per year. Multiply by 100,000 people and you get about 73 million kilograms of food per year. At 40 kilograms per square meter per year, that means you need on the order of 1.8 million square meters of effective growing area. That's about 0.7 square miles if it were laid out flat. But you are not farming flat plains. You're in tunnels and caverns, so you stack it. Build vertical farms with 5 to 10 layers of hydroponic racks inside tall climate-controlled halls. Suddenly your 1.8 million square meters of growing surface might sit inside just a few 100,000 square meters of floor footprint. You could tuck that under a few city blocks, split among multiple modules instead of spreading it over huge surface fields. The farms become towers and deep galleries, not wide fields. Now you have enough green space to feed the city, at least on paper, but the next choice is ugly. Do you bring classic farm animals into this sealed ecosystem, or do you accept that your meat and protein are going to look very different from a typical Earth dinner plate? Large animals like cows are a bad fit for closed systems. They need huge amounts of feed and water, they produce methane and a lot of waste, and then they take up a lot of space. Each kilogram of beef demands many kilograms of plant feed and tons of water over the animal's life. In a Martian city, that cost is almost impossible to justify early on. So the diet shifts. Plants take the front seat for calories and much of the protein. You add insects such as crickets or mealworms, which can convert feed into protein far more efficiently, often better than 1 kilogram of protein for every 2 kilograms of feed. They live in compact stacked trays, use little water, and can eat plant byproducts humans don't want. On top of that, you run bioreactors, microalgae in illuminated tanks, and bacteria in carefully managed cultures grow fast, sometimes doubling their mass in hours. They can produce proteins, oils, and other nutrients with high efficiency. Low gravity helps because large fermentation columns don't sag or stress their supports as much, and mixing can be done with less pumping power. These vertical fermentation towers become protein factories that quietly feed into your food processing lines. For people who want meat-like experience, lab-grown meat from cell cultures offers another route. It is expensive in energy and technology, but it avoids the overhead of whole animals. Over time, as the city's power and manufacturing improve, cultured meat may become a routine part of the diet. By now you can see farms everywhere in the plan. But agriculture is not just a food department bolted to the side of the city, it's a major part of life support itself. So how does that reality change, where you physically put your grow modules and how you move air and heat through them? Plants are natural CO2 scrubbers and oxygen producers. They also add humidity and moderate temperature. That means every greenhouse module is also a life support device. Air from nearby living areas, rich in carbon dioxide from breathing, can be pulled through grow chambers. Plants strip out CO2 and push oxygen back. Moisture from evaporation gets condensed, cleaned, and returned to the water loop. The mass of water, soil, and plant tissue inside agriculture units also acts as a thermal buffer. During the day in your artificial light cycle, they absorb heat. During the night, they release it slowly. That takes peaks and valleys out of your temperature maps, smoothing the load on heaters and coolers. Because of all this, you don't shove farms on the edge of town as a separate district. You embed them deep in the city. Grow towers line main corridors or sit one level over or under housing. Smaller vertical gardens plug into air handling systems in residential zones. People literally walk past glowing, humid stacks of crops on their way to work because those stacks are part of the plumbing that keeps the air breathable and the temperature stable. So by this point, your Martian capital is not just a pile of habitats, it's a tight machine where food, air, water and heat are all cross-linked. But even if you can feed and house everyone, you still have to move them and their cargo safely through a hostile surface, in and out of tunnels and across a planet. So what does streets and highways even mean when the outdoors is basically a vacuum filled with dust? When you step out your front door on Mars, you're not walking onto an open street, so what does going outside even mean if the outside will kill you in seconds? In a Martian city, streets are tubes. The main pedestrian routes are wide, pressurized corridors, maybe 5 to 10 meters across, 16 to 33 feet, running like main arteries between neighborhoods, transit hubs, and industrial zones. Inside, the temperature holds steady around 20 to 23 degrees Celsius, 68 to 73 Fahrenheit. Airflow is kept gentle, under 1 to 2 meters per second, so you feel a light breeze, not a constant draft. Floors are flat, slightly textured for grip in low gravity. Along the sides you have utility trunks, cables, pipes, and emergency gear built into the walls. Lighting is bright but not harsh, tuned to support that 24.6-hour Martian day you set earlier. From these big corridors, smaller side tunnels branch off into residential blocks, quieter and narrower. The overall map doesn't look like a classic street grid anymore. It looks more like a circulatory system, thick main lines feeding thinner branches, all closed, all pressurized. Going for a walk means choosing which tube you move through, not which open street you cross. But people and bags are only half the story. You still need to move tons of cargo, machinery and workers across the city and out into the hostile surface. So how do you design vehicles and transit that fit both a sealed underground maze and a deadly open plain? Outside the habitats in near vacuum and dust, you use pressurized rovers for almost everything. They're like small buses or trucks in sealed shells, running on electric power. They handle mining support, science trips, construction, and maintenance on solar fields and antennas. With low gravity, they can carry heavy payloads without sinking into the ground as much, but they still have to be built to laugh off dust, cold, and radiation. Inside the pressurized network, you don't want big-wheeled trucks sharing the same space as pedestrians all the time. So you add dedicated electric trams or small maglev capsules. These run in their own channels, sometimes in tunnels under the main corridors, sometimes in separated lanes with barriers. Speeds of 40 to 80 kilometers per hour, about 25 to 50 miles per hour are routine. A 10-kilometer trip around 6 miles can take only a few minutes, faster than many Earth subways. Under the rock, you can even run low-pressure or almost vacuum ducts for premium routes. In thin air and low gravity, maglev pods face very little drag. That keeps energy use low and wear on hardware minimal. All of it is electric, so local air pollution inside the city is effectively zero, as long as your power grid holds. Every time one of those vehicles has to pass from inside to outside, it crosses a pressure barrier. And that's where the next problem hits, because those airlocks can literally choke your whole economy if you miscalculate them. So how do you stop the city from being strangled at its own doors? Any movement between the protected interior and the surface must go through airlocks. There's no way around it. For people, you can use small suit locks. For vehicles and cargo, you need big chambers. A large freight airlock might be 10 meters by 10 meters by 20 meters, roughly 33 by 33 by 66 feet. Cycling that volume from full habitat pressure down toward near vacuum and back up again takes time and energy. Even with fast pumps and smart gas recovery, you're looking at 5 to 10 minutes per full cycle if you don't want to waste atmosphere. That means each lock has a maximum number of rovers or cargo loads it can process per hour. City planners have to treat those locks like airport runways or seaport channels. They simulate traffic flows, mining output, ice shipments, construction materials, scientific expeditions, passenger rovers. If you build too few large locks, you hit hard limits. Maybe you can only move a fraction of your mined ice per day, or your construction schedule falls behind because hardware sits waiting in line just to come inside. You can add parallel locks, stagger their sizes, or dedicate some to specific routes, but every one of them costs volume, machinery, and maintenance. Designing them wrong means your city has food, water, and resources sitting useless on the wrong side of a sealed door. And above all those flows, at the edge of the city, you have the biggest choke point of all, the connection to space itself. So where do you put the rocket port when one bad landing could sandblast your entire habitat? You never place major landing pads right next to your pressure hulls. A methane and oxygen rocket, like a Starship-class vehicle, throws out exhaust at high speed, kicking up dust and rocks that can fly like shrapnel. So you push the spaceport several kilometers away, 5 to 10 kilometers, 3 to 6 miles, out on relatively flat basalt plains. The landing and launch pads sit in hardened zones, with deep blast trenches to redirect exhaust. Surrounding them, you build propellant plants that turn Martian water and CO2 into methane and oxygen, large storage tanks, maintenance hangars, spare parts depots, and emergency shelters in case a vehicle fails on the pad. Over time, that whole complex becomes a mini-city of its own, focused purely on flight operations. Cargo and passengers don't walk back to the main city. Robotic flatbed haulers and pressurized shuttles move along dedicated launch corridors, protected routes between the spaceport and the urban core. Those corridors might be trenched, armoured, or even partly buried to limit dust transport and shield the main settlement from any accidents. Inside the planet, people commute by tram and rover. On and off the planet, they ride chemical rockets. But Mars is a whole world, not just one town with a landing pad. So as soon as you get a second and third city, you have to choose. Do you keep burning rockets between them, or do you build something quieter and much more permanent across the surface? For routine travel between Martian cities, rockets are overkill. They use a lot of propellant, they're noisy, and every launch throws dust and exhaust into the environment. Ground transport starts to look better fast, and Mars makes that easier than Earth in some ways. With low gravity and almost no vegetation or liquid water, you can lay long, straight rail lines with shallow cuts and embankments. No forests to clear, fewer landslides, no rivers to bridge. A high-speed maglev line inside a mostly evacuated tube-to-cut air drag can reach speeds of 500 kilometers per hour, about 310 miles per hour with reasonable engineering. At that speed, covering 3,400 kilometers, around 2,100 miles, between two major cities would take under 7 hours. That's basically an intercontinental flight time on Earth, but in a train pinned to the ground. Over a few decades, as more settlements appear, Mars becomes laced with these lines. From orbit, you'd see bright nodes of heat where cities sit, linked by the thin, straight routes where trains run and maintenance stations glow. Each new link adds resilience. If one city has a power issue or crop failure, others can send help by rail. If one spaceport is down, another can take over while passengers and cargo move across the surface. The planet slowly turns into a connected system, not a set of isolated outposts. But every tunnel, every rail, every airlock and landing pad rests on Martian rock and dust. And that rock is not just a platform, it's also your main building material. So the next question is simple and brutal. when almost everything you need is either too far away or too expensive to ship from Earth, how do you turn raw Martian dust into the concrete, glass, metal and plastics of a full-scale alien city? You're not going to build a Martian city out of imported steel and wood. So what does this planet actually give you when you scoop up a handful of its dirt? Rover spectrometers have already told us a lot about Martian regolith. It's rich in silica, iron oxides, aluminum, magnesium, calcium and sulfur. That list should ring a bell because it's basically the ingredient list for your concrete, coal, glass, ceramics and several useful metals. In other words, the dirt around your boots is your main construction supply. The first step is simple and brutal: heat. You can take regolith, dry it, crush it to a uniform grain size, and bake it at temperatures around 1000 to 1200 degrees Celsius, about 1832 to 2192 Fahrenheit. At those temperatures, grains start to fuse together. You can sinter them into the tiles or blocks, or go all the way to melting them into glass. Basic bricks, floor tiles, shielding blocks, and rough internal walls can all be made this way. Instead of flatbed trucks rolling in with prefab panels from Earth, you have ovens and kilns on the edge of the city, feeding a constant stream of regolith into moulds. The quarry is just a shallow pit outside your airlocks. But baking bricks one by one is slow, and Mars gives you something even better: sulfur in the regolith, and a dry, cold environment that suits a very different kind of concrete. So how do you turn that into fast, large-scale building? One of the most promising materials for Mars is sulfur concrete. Sulfur exists in Martian rocks and soil. You mine it, purify it, and heat it until it melts. Then you mix that molten sulfur with regolith at the right ratio and pour it into forms. As it cools, it solidifies into a tough, waterless concrete. No liquid water needed, which is perfect in a place where every litre is precious. Tests on Earth show that sulfur concrete can reach compressive strengths over 50 megapascals, in the same range as many standard concretes you use for buildings and bridges. It also handles Mars-like conditions well, since there's no liquid water to cause long-term chemical breakdown. Once you have that material, you move to automation. Giant 3D printers mounted on robotic gantries can extrude sulfur concrete layer by layer. They lay down continuous walls, arches, and even simple domes at a rate of a few cubic meters per hour. A small habitat shell or a section of tunnel lining can go from design file to finished structure in days instead of months. You still need to add internal insulation, pressure liners, and life support gear, but the heavy shell is local and fast. Bricks and sulfur shells cover the basics, but a real city needs metal frames, strong tools, rails, and pressure-rated hardware. So how do you get metal from a landscape that mostly looks like rusted dust? Martian rust is a gift. The red colour of the surface comes from iron oxides. If you feed those oxides into reduction reactors with hydrogen or carbon monoxide, you strip the oxygen away and are left with metallic iron. That iron can be cast into simple shapes, rolled into bars, or combined with small amounts of imported alloying elements to make better steels. Silicon is another key target. Silica sand, which is also common, is your main source. Smelting it takes high temperatures and a lot of energy, usually by mixing silica with carbon and heating until the oxygen leaves as carbon monoxide or dioxide, leaving silicon metal behind. From this, you get both structural alloys and the base for electronics and high-quality glass. Aluminum and magnesium are trickier. Their ores are there, but the energy cost to pull pure metals out is high. Early on, you might import these in limited amounts for critical parts. As your city's power grid climbs into the hundreds of megawatts, large-scale refining of aluminum and magnesium becomes realistic on Mars itself. At that point, you can build lightweight alloys for vehicle frames, pressure vessel rings, and high-performance structures. The architecture begins to shift from crude, thick shells to more refined, high-tech designs. Metals and concrete get you far, but a modern city also runs on plastics, seals, and composites, and Mars does not have oil fields. So how do you manufacture all that chemistry from a thin CO2 atmosphere and some ice? Your core carbon source is the Martian atmosphere. It's about 95% carbon dioxide. You already pull that in for oxygen production and fuel. Sabatier reactors combine hydrogen from water with CO2 to make methane and water. That methane is not just rocket fuel, it's also a base chemical for plastics. Split or reform it to get carbon-rich gases. With additional processing, such as Fischer-Tropsch systems, you can turn carbon monoxide and hydrogen into longer-chain hydrocarbons, the building blocks of synthetic waxes, oils, and polymers. From there, you can produce common plastics for piping, insulation, packaging, and interior panels. For high-end structural composites, you push further. You can make carbon fibers from certain polymer precursors derived from that same synthetic chemistry. At the same time, you can melt basaltic regolith and draw it into fibers similar to fiberglass. Combine carbon fibers and basalt fibers in resin matrices and you get hybrid composites with very high strength to weight ratios, perfect for beams, interior pressure hulls, and lightweight panels. These materials can rival aerospace composites used on Earth, but their raw atoms all come from Martian CO2, water ice, and rock. Even with all that in place, you still can't afford to waste anything. Every kilogram you flew in from Earth was insanely expensive, and even local material costs you power and machine time. So how do you keep the city from slowly drowning in its own construction scrap and obsolete hardware? You treat construction waste the same way you treat air and water as part of a closed loop. Old pressure hulls, when retired, don't get dumped. They are cut up, melted down and recast as new structural members or shredded as aggregate for new concrete. Broken glass panels go back into furnaces to be remelted. Worn-out plastic parts are fed into depolymerization systems that break them back into monomers or simple hydrocarbons, ready to be turned into fresh plastic. Every major construction site is tied into a material tracking system. You log how much regolith you pull in, how much sulfur, metal, and glass you produce, and how much scrap comes back. If a waste stream spikes, it triggers a review, the same way a spike in water loss or air leakage would. Over time, the look of the city shifts. In the early years, you see a lot of Earth-made modules, shiny alloys, and white composites. As local production takes over, more surfaces are dark regolith concrete, cast glass, and raw basalt textures. Later still, as Martian industry matures, you see sleek composite spans, light alloy trusses, and complex 3D printed forms everywhere, all made from local feedstock. The planet's own chemistry becomes your palette. But even the best materials can't protect you from everything Mars throws at you. Dust, temperature swings, quakes, and impacts all hit your city sooner or later, so the next step is blunt. Now that you've built this whole structure out of Martian rock and chemistry, how do you keep it from slowly being sandblasted, cracked, frozen, and punched full of holes by the planet itself? You've built your Martian city out of rock and metal, but now the planet starts fighting back, so how dangerous are its storms and quakes really? And which threats are actually the ones that can kill the city slowly? Start with the famous dust storms. They're huge, they wrap the whole planet, but they are not the hurricane-force wrecking balls you see in movies. The key is air density. Martian air is only around 1% as dense as Earth's, roughly 0.015 kilograms per cubic meter. So a wind gust at 30 meters per second, about 67 miles per hour, sounds scary, but because the air is so thin, the push on a wall is closer to what a 3 meter per second breeze around 7 miles per hour would feel like on Earth. Your buildings are not going to topple from dynamic pressure alone if they're even half decently engineered. The real danger is abrasion. Tiny dust grains moving fast act like sandpaper over years. Surfaces get pitted, coatings wear off, seals slowly erode. To fight that, you choose tough exterior coatings, hard ceramics, and sacrificial outer layers designed to take the beating and be replaced. Hinges, joints, and external moving parts are kept to a minimum or tucked behind shields. The city doesn't fear being blown over, it fears being ground down. But dust doesn't just hit walls, it tries to get inside everything, including your lungs and electronics. So how do you keep an entire city clean when the outside world is made of toxic electrostatic powder that wants to stick to every surface? Martian dust particles are very small, often less than 10 micrometers across, much finer than typical Earth sand. They can stay suspended in the thin air for a long time, and they pick up electric charge easily, which makes them cling to suits, vehicles, windows, and instruments. Many samples also show perchlorates and sharp silicate grains, which are both bad news for human tissue and for hardware. Inside the city, heating and cooling systems have to run close to Earth cleanroom standards. Filters are HEPA grade or better, catching particles down into the sub-micrometer range. Airflow paths are designed so that dust is pulled toward filters and not allowed to settle in dead corners. Every airlock is also a cleaning station. When someone or something comes in from outside, you don't just equalize pressure and open the door. You run dust removal steps. Rotating brushes knock off loose grains. Electrostatic plates pull charged dust from suit surfaces. Maybe acoustic or vibration systems shake stubborn particles out of cracks. Only after a good cleaning does the inner door open. If you skip that, dust builds up indoors, people breathe perchlorate-contaminated particles, and electronic boards get coated in conductive abrasive powder. That leads to health issues and hardware failures. Keeping dust out becomes as vital as keeping air in. Meanwhile, the solid ground under your city is not completely quiet. Mars has Marsquakes and meteor impacts. So how do you make sure that one bad shake doesn't turn your pressure shells into a network of hairline cracks? NASA's InSight lander recorded hundreds of Marsquakes, some above magnitude 4. That's not giant by Earth standards, but remember your structures are pressurized shells, not just simple buildings. A crack that wouldn't matter in an Earth apartment block can be a serious leak path on Mars. Most of your habitats are buried, which helps. The soil around them damps a lot of horizontal shaking. But you can't count on perfectly gentle motion. You design pressure shells with flexible joints, sliding supports, and expansion gaps so they can move a few millimeters or even centimeters relative to their foundations without tearing. Pipes and cables include loops or flexible segments so they don't snap when the ground shifts a little. On top of natural quakes, you also worry about impacts. Smaller meteorites that burn up in Earth's thick atmosphere can reach the surface on Mars. That adds sudden jolts and pressure waves that your structures have to ride out. So structural dynamics, not just static strength, become a big piece of your engineering. And then there's temperature. The surface can lurch from extremely cold to insanely cold in one sol. So what does that do to metal beams, glass panels, and seals that cross from the open environment into your warm interior? At some sites, surface temperatures might swing 60 to 80 degrees Celsius in a single Martian day, say from -20 to -90 Celsius, about -4 to -130 Fahrenheit. Metals expand when they warm and contract when they cool. Glass does too, and at different rates. If you built everything with tight, rigid joints and long straight seams, those daily expansions and contractions would open gaps, crush fasteners or crack panels, so you design big forgiving joints. Interfaces between materials are zigzagged or stepped, not straight, so stress spreads over a wider area. You use multi-layer composites where different layers share and damp the movement. Most of the city lives a few meters underground, partly for this reason. At that depth, temperatures are far more stable, maybe hovering around -20 to -40 Celsius, -4 to -40 Fahrenheit year-round. It's still cold, but it doesn't whiplash back and forth every day. Your pressure shells then only see large swings on the inside face where you control the climate, not on both sides at once. Even with quakes handled and temperature swings tamed, you still can't ignore the sky completely, because there is no thick atmosphere to burn up incoming rocks, so how do you make sure that one unlucky space bullet doesn't end the whole experiment? On Earth, many small meteoroids explode or vaporize in the upper air. On Mars, much more of that material reaches the ground. The chance of any 1 square kilometre being hit by a dangerous impact in a given year is low, but your city and its surrounding infrastructure cover thousands of square kilometres when you add in solar fields, mining sites and rail lines. Over decades, the risk adds up. You respond by armouring the tops of important structures. 3 or more meters of regolith over main habitats not only blocks radiation, it also absorbs the energy of small impacts. A rock that would punch through a thin roof barely makes a dent in that much soil. Critical systems like main life support plants, data centers, and reactor controls are placed deep underground or separated from each other so that one strike can't wipe out all copies. If a small meteor hits on the outskirts, it might dig a shallow crater, damage a solar array, or sever a secondary pipeline. That's bad, but it's a repair job, not an extinction event. Redundancy and spacing are your tools. No single building or cable run is allowed to be the one point of failure that takes down the city, so by now, you've armoured the city against dust, shaking ground, wild temperature swings, and falling rocks. Physically it can last. But the people inside it are not robots. They live in tunnels on a 40-minute time lag from Earth, under a false sky for years. That raises the next, maybe hardest problem of all. Even if you get all the physics right, what does long-term life in this kind of sealed, alien environment do to the human brain? And how do you shape the city so that the people inside it don't slowly break? You can armour a city against radiation and quakes, but if the people inside can't sleep, can't think straight, and start to hate the place, the city still fails. So how does Mars mess with your brain, starting with something as basic as the length of the day? Your internal clock is tuned to about 24 hours. Mars gives you a soul that's around 24 hours and 39 minutes. That 39-minute difference sounds tiny, but if you ignore it, it drifts. In 2 weeks, your body's midnight can end up in the middle of your official workday. Sleep gets fragmented, reaction times drop, mood goes down. So the city doesn't leave this to chance. It hard-codes light control into the architecture. Indoor lighting systems run on a 24.6-hour cycle. In the morning phase, lights come up a bit cooler and more blue-rich, signalling wake time to your brain. During the day, they stay bright and neutral. In the evening, they shift warmer and dimmer, slowly stepping you down towards sleep. Work shifts, school classes, public transit schedules, medical check-ins, all sync to that Martian sun soul, not an Earth clock. You're not living on Houston time anymore, you're living on local planetary time by design. New arrivals from Earth get a managed adjustment period where their lights and schedules are nudged day by day into the sol rhythm, so jet lag doesn't stretch on for weeks. Once you lock in the day length, the next hit comes from the environment itself, because you're living in carved rock and metal shells, with the same colours and sounds repeating every day. So how do you stop that from turning into a sensory prison that wears people down? Long-duration studies in places like Antarctic stations and submarines show the same pattern. Monotony is corrosive. When every hallway looks the same, sounds the same, and smells the same, stress and depression climb. A Martian city is basically one big remote base, so it has to fight that effect deliberately. You do it with controlled variety. Wall panels aren't just bare metal and white plastic. You use wood-like textures, colour accents, and different surface finishes from one zone to another, so each district has a recognisable feel. Plant walls go into key corridors and public spaces, not just into greenhouses, so people see real leaves and smell real soil on normal walks, not only during scheduled visits to farms. Ceilings are shaped, not just flat ducts. Some arcs, some gentle curves, some higher segments over plazas. You manage sound too. Machinery hum and fan noise get masked with low-level background audio, tuned to be more like distant wind, water, or subtle ambient tones instead of raw mechanical drone. Loud alarms and harsh sounds are reserved for true emergencies, so they stand out immediately. Lighting colour, panel textures, and sound profiles rotate subtly by area and by season. People moving from work to home or to recreation feel clear changes in environment, even though they never see the real outside directly most of the time. But even a nice wall and good lighting don't change one core fact. Everyone is packed inside a finite volume of air and rock, and humans handle crowding badly, so how do you keep population density from turning your capital into a pressure cooker? We know from Earth data that once usable living and public space per person drops too low, stress, conflict, and mental health problems increase. On Mars, you can't just sprawl to fix that. Every cubic meter you pressurize costs you construction, shielding, and life support. So you carefully balance private and shared space. Private living cabins might be only 10 to 20 square meters each, around 100 to 200 square feet, compact but functional. A bed, a workstation, storage, maybe a tiny wash area. That's tight. And if that was all people had, it would crush morale. The city compensates by making shared zones generous. You build internal parks under small domes or tall caverns, with trees, benches, and open walking space. You add gyms, sports halls, libraries, cafes, maker spaces, and quiet lounges. These third places are where people can exist without a fixed role, not at work, not at home, just present. The city layout supports this. Every residential cluster sits within easy walking distance of multiple shared spaces. Crowding metrics are monitored. If the average person only has a few square meters of breathing room in public areas, that's a warning sign. Planners treat square meters per person as seriously as they treat kilowatts per person or liters of water per person. It's not luxury, it's stability. Even with all that, you still hit a hard structural limit. You can't put real windows everywhere. Rock and radiation shielding block most views, so how do you stop people from feeling like they live in an endless box with no horizon? You fake windows, but you fake them carefully. High-resolution display panels set into walls where windows would normally be show views from external cameras mounted around the city and on nearby hills. You can see real Martian landscapes, updated in real time or with slight delays, complete with changing light and dust levels. Some windows show live Earth scenes, oceans, forests, cities. Others show artistic or abstract visuals. The key is that they change. Static posters don't trick the brain for long. Moving, time-varying scenes with real depth cues help more. Audio's part of it too. You pipe in actual Mars wind noise recorded outside, mixed at safe levels, along with optional nature soundscapes people can select in their cabins. For deeper immersion, some rooms and public pods offer full VR or large wraparound displays where people can step into a beach, a forest, or a night sky that doesn't look like a dim red dot overhead. It's artificial, yes, but studies on simulated nature show that even fake environments can lower stress markers and improve mood if done well. The city leans on that heavily. All of this environment tuning still only sets the stage. What really decides whether people feel like they belong or like they're trapped is culture. So how do you turn a survival outpost into a place that actually has its own identity, rituals, and reasons to care? Remote crews on Earth show a clear pattern. Shared rituals and traditions hold groups together. Weekly dinners, holiday events, small ceremonies around milestones. A Martian city scales that up. It builds its own calendar into daily life. The day the first crew landed becomes a citywide holiday every year. The first harvest from local greenhouses is celebrated. The first child born in the city, the first intercity rail link, the first local election result. These all become fixed points in the culture. People get time off, events are scheduled, and physical spaces are built to host them. You see this in the layout. Central plazas are sized to hold big gatherings. Amphitheatre-like spaces get carved into rock, good for speeches, performances, or memorials. Certain long corridors with good acoustics and lighting are designed as processional routes for festivals. Public art, flags, symbols, and signage reflect local history, not just Earth nations or company logos. Over time, the city starts to feel like it expects people not just to endure life there, but to actually live it, with birthdays, graduations, protests, concerts, and quiet evenings all included. That cultural layer is as important as the oxygen system. Without it, the place is just a machine. With it, it starts to be a society. But that society still sits in a legal vacuum. Earth's laws were written for land, oceans, and air, not buried tunnels on another world, so the next hard question is this. When you have a whole city where one broken valve can kill hundreds of people, who actually has the right to give orders, to lock doors, to control resources, and to say what ownership even means on Mars? You can keep people alive with air, water, and food, but if no one knows who's in charge or what rules actually apply, the city is a ticking bomb. So who really owns a Martian capital under Earth law? Right now, the main legal framework is the 1967 Outer Space Treaty. It says that no nation can claim sovereignty over the moon or other celestial bodies. In plain language, no country can officially say this piece of Mars is now part of my territory the way they do on Earth. So your Martian city is not a classic country. It sits in a grey zone. It might be built by a company registered in one nation, crewed by people from multiple nations using hardware funded by others, all under international agreements. You end up with a mix of international space law, corporate charters, and whatever local governance everyone agrees to follow. That legal tension shows up physically. You need secure government and admin spaces, offices for city councils or boards, rooms for arbitration and courts, archives for contracts and regulations. You also need strong communication hubs that link back to Earth governments, regulators, and agencies, because disputes will cross planets. Zoning has a legal side. Certain blocks might be under direct corporate control, others under local self-governance, others reserved for international treaty operations like scientific neutral zones or emergency facilities. When you walk through the central district, you're not just moving through architecture, you're crossing invisible legal borders. But law on Mars is not just about who owns which office. In a city where one broken valve can kill hundreds, someone must have the legal power to act fast, even against individual wishes. So how do you bake emergency authority into the actual layout of doors and corridors? Bulkhead doors, lockdown systems, and isolation modes are not only engineering tools. They're physical extensions of legal power. The question is, who gets to use them, and under what rules? If a sensor detects a pressure drop in one tunnel, somebody has to make a call, seal that section and trap a few people on the wrong side or risk a larger leak that could spread. That decision cannot be improvised every time. Protocols must be clear, written, and agreed in advance, but there will be defined roles. Duty officers, safety controllers, maybe a mayor or governor with specific emergency powers. The city layout reflects that. You design redundant escape routes so people can get out of danger without going through a single choke point. At the same time, you intentionally create a few control points where security can stop movement in or out if needed. For example, around reactor zones, central life support plants, or the main data cores. Those control points turn a legal order like Lockdown Sector 3 into an immediate physical reality. This also touches rights. On Earth, freedom of movement is taken for granted in many places. On Mars, that right has to be balanced against survival. The law has to say clearly when someone can be confined for their own safety or for the safety of others, and how long that can last. The walls enforce those decisions. Under all of that lie more basic questions. What does it even mean to own property in a place where your house is welded into everyone else's life support? You can't have a classic standalone house in vacuum. Your room depends on continuous pressure, air, water, and power from shared systems. If you walk away and stop maintaining your section, you don't just risk your own walls, you may put neighbours at risk. So property ends up looking closer to co-ops or condominiums than detached homes. You might own or lease the interior space of a cabin or a set of rooms. You might have long-term usage rights to parts of corridors, storage units, or even agricultural racks. But the outer hull, the pressure lining, core life support plants, and shared infrastructure behave legally, like utilities or like the common elements in a big condo building. Contracts spell out how much you pay for maintenance, what share of upgrade costs you carry, what happens if you damage shared systems, and how expansion is funded. Want to add a new private module? You need engineering approval and legal approval because your extra space changes the load on shared air and water loops. Where there is property and stress, there is also crime. But on Mars, a single act of sabotage or careless vandalism can be lethal for an entire block, so how far does the city go with sensors and surveillance? And how much privacy can you realistically keep? In a high-risk, closed environment, sensors are everywhere by default. Pressure, temperature, gas mix, vibration, and power use are all constantly monitored. Cameras watch airlocks and key corridors to verify procedures. Equipment logs every access. Even if the city never set out to watch people, the infrastructure is already halfway there. Because sabotage or serious tampering is existential, the city leans toward heavy passive surveillance. Software looks for anomalies, someone opening a maintenance panel at odd hours, strange access patterns in reactor rooms, unexpected crowds near critical hubs. Security teams act on those flags fast. At the same time, you cannot treat residents like prisoners without blowing up morale. So architects and planners carve out privacy pockets on purpose. Quiet rooms with acoustic insulation, cabin areas where visual surveillance is limited or absent and only environmental sensors run. Zones in public spaces where seating and layout give people line-of-sight control over who can see them. Rules about data use matter. Residents will want to know what is recorded, how long it's kept, and who can see it. The legal system has to define when security can override normal privacy protections, for example, when there is a credible threat to life support systems. In a Martian city, privacy is not absolute, but it's also not zero. It's a constant negotiation. All of this gets more complicated as the headcount climbs. A tiny outpost can run on handshakes. A real city cannot. So how does governance evolve physically as you grow from a few hundred people to tens of thousands? With 200 residents, you can literally gather everyone in one hall, take votes by hand and hash out rules in person. That kind of direct democracy is slow, but workable at that size. At 20,000 it fails. Not everyone can be in the same room or even in the same debate channel. The city's core starts to show that shift. Assembly halls get bigger and more formal. Instead of one multi-purpose meeting room, you build a council complex with multiple chambers, offices for representatives, and staff work areas. Media studios appear, broadcasting sessions and announcements across the local network. Translation booths, legal libraries, and secure archives all take up space. Laws become more detailed. You get formal building codes, life support standards, radiation exposure limits, labour rules for high-risk jobs, and regulations on work shifts in low G. Enforcement agencies need control centres, holding rooms, evidence storage, all of that is real architecture. Walk through the central district of a mature Martian city, and you can tell what kind of system it has become. A tight, glossy corporate enclave will look and feel very different from a research-driven commune or a more open, semi-democratic settlement. The style of buildings, the accessibility of public halls, and even the number of visible security checkpoints all tell you who really runs the place. But whoever is in charge, the city still has to pay its bills, whether in money, energy, or raw materials. You cannot just be a science camp forever. So the next question cuts right to the core. Once the basics are stable, what is this Martian capital actually for? What does it sell? Who does it serve? And how does that economic purpose reshape the streets and tunnels you just built? Once the city stops worrying about dying every week, it has to answer a blunt question. Why does it exist at all? What is it actually for? In the beginning, the answer is simple: science. The first version of this city is a research base scaled up. You have geology labs analysing core samples, trying to map the planet's history. Astrobiology cleanrooms run ultra-sterile experiments on ice cores, rock fractures and dust, hunting for any sign that life ever appeared here, even at the microbial level. Atmospheric observatories track trace gases like methane and hydrogen, looking for patterns that might hint at active chemistry underground. Those early buildings are mostly labs, sample storage, instrument silos and data links back to Earth. But as soon as the basics of life support and power are reliable, something else starts to dominate: industry. Mining rigs move further out, pulling water ice for propellant and life support, scraping iron-rich regolith for metals, and, if surveys are lucky, tapping into more concentrated ores, including possible platinum group metals. The city's economy shifts from science outpost to resource base. The look changes: more processing plants, more ore storage, more refinery modules, more heavy equipment yards. Tourism does appear, but not as the main driver. A trickle of ultra-rich visitors fly in, paying enormous amounts to spend a few weeks living on Mars, walking in low gravity, and broadcasting from another planet. That money is real. The numbers are small compared to what mining and local industry bring in. Tourism is a boutique layer, not the core, but exporting metal and propellant back to Earth is brutally expensive. Every kilogram you want to send home needs multiple kilograms of fuel and a full launch vehicle. So if you can't move much mass, what can this city sell to the rest of humanity that doesn't weigh anything? The answer is information, not bulk cargo. Data is effectively weightless. You can beam it by radio or laser back to Earth for a tiny fraction of the cost of shipping physical goods. So the city's most valuable exports may be intellectual, new materials designed and stress-tested in low gravity and harsh conditions, biotech results from experiments on how microbes, plants and human cells behave in 0.38 G, software and AI systems built to run critical infrastructure with high reliability and low human intervention, operational know-how on how to manage large closed-loop systems and multi-year missions, and culture, music, films, streams and games created by people who grew up under a red sky inside tunnels will not look or sound like anything from Earth. A Martian band streaming regular concerts or a drama series shot entirely in low gravity might pull huge audiences at home. That kind of export costs the city almost nothing in mass and energy compared to ore, but could be extremely valuable. While that happens, an internal economy grows whether you want it or not, because even in a closed loop, people specialize and trade. So how does that show up in the actual layout of the city? Different districts begin to form. One area near the industrial edge focuses on manufacturing. 3D printing halls, machining shops, composite layup rooms, robot repair bays. From outside you see tall exhaust and intake stacks tied into scrubbers and filters, loading docks for cargo trams, and large doors sized for vehicles and modules. Another district is dominated by agriculture, packed with agri-domes, vertical grow towers, nutrient processing plants, and water handling hardware. Humidity fogs some windows. You see green light leaking from grow rooms during the night cycle. A quieter district houses research labs, education centres, and data infrastructure. These blocks carry thicker bundles of fibre optic cables and more antenna feeds, fewer heavy cranes. Server rooms and sensor labs replace ore silos and bulk tanks. People in each zone offer services to other zones: maintenance contracts, energy allocations, food deliveries, medical support, education, entertainment. Even if the external trade is limited, internal trade is real. You can price it in a local credit system, in earth currencies, or in some hybrid, but the effect is the same. The city turns into an economic network, not just a budget line in an earth agency's accounts. Underneath all those transactions, one resource quietly drives every decision: energy. On Mars, where every watt is fought for, power becomes the real hard currency. So how does that change how neighbourhoods and buildings compete and grow? In this environment, megawatt hours feel like cash. Every greenhouse, factory and lab has a power budget. City planners decide whether extra energy goes into expanding housing, boosting food production, or running high-end VR and entertainment systems. If there's a surplus, maybe you spin up more data centers to sell computing time back to Earth. If there's a shortage, you cut back non-essential lighting and bandwidth. Buildings start to advertise their efficiency the way Earth buildings brag about luxury. A net positive residential block that produces more power than it uses, thanks to rooftop solar and heat recovery systems, is attractive and may earn credits by feeding excess into the main grid. Districts compete to reduce their energy intensity per person or per kilogram of product. That competition is not just good PR, it's survival. Efficient districts get priority when decisions about expansion are made. In some scenarios, citizens even see part of their income or ration in energy terms. So many kilowatt hours per month allocated to their cabin for lighting, computing and personal tools. Go over that and you pay more. Stay under and you can trade the difference. The city's invisible budget is measured in power first, everything else second. Then you hit the real test of any economy. What happens when something goes wrong far away? One failed rocket on Earth, one launch pad explosion, and resupply might be cut for a year. So how does the city's physical layout and industry plan absorb that kind of shock without collapsing? First, you build reserves. Warehouses near key hubs store months of critical spares: air and water filters, pump parts, suit seals, electronics, medical supplies. Not everything, but the components that are hardest to improvise. Food reserves are baked into extra greenhouse capacity and dry stores. Second, you lean on flexibility. Shadow factories are manufacturing spaces with general-purpose 3D printers, CNC machines, and modular assembly lines. In normal times, they handle custom jobs and small series. In a supply crisis, they flip into emergency mode, switching to produce parts that used to come from Earth. That only works if you've already stored the raw materials and designed blueprints and tested the recipes. Third, you design life support with redundancy. Multiple greenhouse modules with overlapping crop mixes, several independent water treatment and oxygen production lines. If you lose one, the others can cover essentials, even if variety drops and everyone's diet gets more basic. In a major disruption, luxuries go first. High bandwidth entertainment, travel, non-critical research, imported treats from Earth, all cut back or pause. The city falls back to a survival mode layout. Only essential corridors fully lit, non-critical workshops idle, strict energy caps across the board. It's harsh, but people live. When supply lines recover, you ramp back up. So by now, the Martian capital is not just surviving day to day, it has a purpose, an economy, and some shock resistance. The next step is unavoidable. Once one city proves it can work, more follow. Then the question stops being about a single settlement and flips to something much bigger. How do you scale from one buried city to a whole network of Martian civilization without breaking the environment or the economy that hold it together? Once one Martian city works, it doesn't stay small for long. So what happens when population starts climbing faster than your life support can comfortably handle? Say you start with 100 people. If that population doubles roughly every 10 years through immigration and births, in 50 years you're at about 3,200. In 100 years, you're above 100,000. That sounds impressive, but the planet does not care how many humans you want to drop on it. Your real limit is carrying capacity, how many people your infrastructure can support at a stable level. That depends on three things growing fast enough: floor area, power output, and the efficiency of your closed-loop systems for water, air, and food. If population grows faster than those three, you hit hard walls. Water processors max out. Greenhouses cannot deliver enough calories. Housing density pushes past healthy limits. So expansion can't just mean more people. Before each big wave of arrivals, you dig new tunnels, add new shielded levels, scale power from, say, a few dozen megawatts toward the hundreds, and upgrade recycling from 95% to 98 or 99%. The ugly truth is that infrastructure has to grow ahead of population, not behind it. If you get that backwards, you don't get a bustling city, you get shortages and rationing. Once the first city proves that this balance is possible, more settlements appear. And here's the key. The second and third cities do not look like clones, they specialize. So how does that change the whole planet's layout? One follow-up city might sit right on top of a massive ice deposit built around water and propellant production. It's less glamorous, more industrial, with huge electrolyzer plants, tank farms, and launch depots sending methane and oxygen to other bases. Another might anchor itself on the rim of Valle Marineri, the giant canyon system optimized for tourism and science, with observation decks looking out over cliffs 7 kilometers deep, about 4 miles. That city sells views, geology, and research capacity more than bulk fuel. High-speed rail or maglev lines link these hubs. What used to be isolated dots on maps turn into a network. From orbit, each city shows up as a bright cluster of infrared heat against the cold background, with thin glowing lines connecting them where trains run and power and data move. Mars starts looking less like an empty rock and more like a young circuit board. As populations across these cities grow into the millions, the projects you even consider start to look planetary in scale. So what kind of mega infrastructure do you see when a whole world starts to adapt itself to human needs? With millions of residents, individual greenhouses and small solar fields are no longer enough. You might put mirrored arrays or light collectors in orbit, angled to bounce extra sunlight down onto agricultural regions, giving farms more effective light without having to cover more ground in LEDs. On the surface near cities, You could build large electrostatic or magnetic fence systems designed to strip dust out of low-level air currents, reducing how much fine material gets lofted during storms. That might shrink local storm intensity, or at least protect key infrastructure fields. CO2 capture plants on an even larger scale could slowly tweak the atmosphere over centuries, either thickening it a bit to improve pressure and temperature, or moving it toward a different composition around cities. Each of these projects needs its own power nodes, maintenance depots, worker housing and logistics lines. The result is spine-like corridors and big service hubs spread across thousands of kilometers. From above, humanity's presence becomes visible not just as cities, but as these huge engineered scars and grids. While the hardware scales up, the culture diverges. After a century in a low-gravity underground red sky environment, Martian civilization is not just Earth, but elsewhere. So how does that show up in the stone, steel and habits of daily life? Architecture shifts away from imported Earth styles. Local materials and constraints drive new aesthetics. You might see a lot of black basalt cladding, red regolith tiles, and cool white composites as standard colours. Curved, thick walls and arched ceilings are normal because they handle pressure and radiation best. Public art uses light, shadow and low-gravity motion in ways that feel strange to Earth visitors. New philosophical movements emerge shaped by a constant dependence on machinery and by the view of a tiny, distant sun. Their meditation halls are designed around silence, very low lighting, controlled echoes in tunnels and perhaps partial G-zones. Main streets and plazas host festivals that only make their nears in 0.38 G, with dances, processions and sports built around long, slow jumps and gentle falls. Walk through a mature Martian capital, and it doesn't feel like a transplanted Earth city. It has its own proportions, its own colour palette, its own rhythm shaped by souls and low gravity. It looks and feels Martian in a way that's hard to fake anywhere else. With multiple big cities, each with its own character and resources, you run into the same problem Earth did: conflicts over water, power and territory. Only here the stakes include life support. So how do these settlements stop resource disputes from turning into something much worse? And what does the first Martian law actually look like? If two cities draw from the same buried ice field, there has to be an agreed upon extraction rate. If one settlement runs reactors that affect shared rail lines or grid links, regulations are needed. Radiation exposure standards, worker safety rules, and environmental limits can't be allowed to drift wildly from city to city, or you start seeing safety havens and sacrifice zones emerge. To handle that, Martian cities create joint assemblies. Neutral meeting hubs are built, sometimes literally halfway along the main rail lines between major cities. Some might be rotating conference stations in low Mars orbit, offering near-Earth G for delegates. Others could be ground-based, heavily shielded complexes designated as neutral territory. These places house legislative chambers, arbitration courts, and treaty offices. Their architecture is deliberately symbolic. Vaulted halls balance partial gravity floors so everyone, Earthborn and Marsborn, can stand comfortably. Walls inscribed with multilingual agreements and the names of founding cities. Here, inter-city rules are debated and signed. Who can tap shared aquifers? How to compensate for industrial accidents that blow dust or radiation across borders? How to allocate rail capacity? And what happens when a city wants to leave a union or form a new one? Over time, these agreements crystallize into something recognizably Martian law, distinct from Earth treaties, tuned to pressure hulls, radiation limits, water rights in ice fields, and energy budgets in a thin-air world. The institutions that uphold those laws and the buildings they occupy become the Capitol Hill of Mars. At that point, Mars is no longer a single experiment. It's a small civilization with its own physics and economics. And that leads to one last bigger question. Once you know how to build and run a whole world like this, what happens when you take those same design rules and start applying them off Mars, to the Moon, to asteroids, and even to the idea of slowly reshaping whole planets themselves? Once you know how to run a buried city on Mars without killing everyone, You're basically holding a test kit for the rest of the solar system, so what does Mars actually teach you about building cities where humans should not exist at all? By the time a Martian capital is mature, it's a prototype. The core patterns are clear. You bury habitats under meters of regolith or rock for radiation protection. You rely on thick shielding instead of atmosphere. You run tight, closed-loop systems for air and water, with recycling efficiencies pushing toward 98 or 99%. Your power grid is a hybrid, solar on the surface whenever light is available, nuclear as a constant base with big storage buffers in between. Every major failure you survive becomes a lesson. Fragile glass domes that cracked or dusted over too fast don't get copied. Underbuilt storage that almost starved the city during a bad launch year becomes a warning in every later design. Times when planners ignored psychology and crammed people into monotonous, cramped tunnels show up in future checklists as never again. Those patterns and those warnings form a set of blueprints. You can now hand them to engineers planning a base on Titan, or under Europa's ice, or around an asteroid, and say, start from here, then adjust the numbers. Mars becomes the reference manual for off-world living. Different worlds, different for physics, same basic fight, life support versus vacuum. So how do those Martian lessons change when you move to places like the Moon or small asteroids? The Moon has got about 1/6 of Earth's gravity, harsher radiation than Mars, and brutal 2-week days followed by 2-week nights. Asteroids have microgravity, essentially 0 G, and often only a loose layer of dust instead of a deep regolith blanket. But the core math you used on Mars still works. You still need closed-loop water and air systems. The same recovery percentages and leak budgets apply. You still need to shield against cosmic rays and solar storms, though on the Moon you might lean even harder on thick rock and possibly lava tubes. Your power budget still has to match life support and industry, though the mix changes. On the Moon, 14-day nights push you toward more nuclear or huge energy storage. On asteroids, far from the Sun, solar weakens and nuclear or mirrored collectors dominate. Structurally, you swap gravity numbers in your calculations. 1/6 G on the Moon allows even lighter structures than Mars. Microgravity on asteroids pushes you toward rotating habitats for artificial G and makes internal up and down mostly arbitrary. Economic models get new inputs, different mining yields, different transport costs, different local raw materials. But you're not starting from scratch. You're adjusting a Mars-proven template. Back on Mars, there's a big, slower lever your cities are pulling without always meaning to: climate. Every time you build, mine, and burn, you touch the atmosphere. So how do city-scale decisions add up to something that looks a lot like terraforming? Terraforming Mars sounds like one giant unified project, but it really starts with local choices. How much CO2 do you dump or pull from the air during industrial processes? Do you build dark surfaces that absorb heat and maybe accelerate local warming, or bright surfaces that reflect sunlight? Do you intentionally vent certain gases that trap heat even a little, just to make conditions near your cities slightly less harsh over time? Even a small average temperature increase, 2 to 5 degrees Celsius, 3.6 to 9 Fahrenheit, changes how stable liquid water can be near the surface in some regions, how often frost forms, and how often CO2 freezes out. One city's decisions barely move the needle, but dozens of cities, each running reactors, greenhouses, and chemical plants for centuries, can cumulatively shift atmospheric pressure and temperature. That means urban planning on Mars and global climate engineering are not separate issues. Your cities are engines that over long time scales push Mars in one direction or another, even if no single generation ever sees a fully terraformed world. Zoom back into the city itself and ask the practical question. After all these sections, what does a fully mature Martian capital actually look and feel like if you walk it end to end? From the surface, it is not a fairy tale glass dome. It looks more like a layered machine. On top, you see industrial skin, solar fields, radiator farms, antenna arrays, access hatches, rover depots, mining links. A few scattered domes and towers poke up, mostly for specific uses like small parks, observation decks, or communication masts. Just below that skin, inside thick regolith armoured levels, you have the main functional layers. Industry and heavy transit live here. Rail lines, maglev tubes, machine halls, fabrication plants, big greenhouses stacked in vertical farms, water and air processing cores and storage tanks. This mid-zone is dense, out in some parts, and threaded with utility tunnels. Deeper still, in the most shielded cores, you find storm shelters, main data centres, medical centres, and high-gravity centrifuge rings where people train and recover in near 1G. These are the safest places on the planet during a solar flare and the most controlled in terms of environment. Inside all that, your daily path might go like this. You leave a small private cabin in a warm residential tunnel, walk through a plaza under a modest dome where kids are playing low-G ball games, pass by tall vertical racks of LED-lit crops behind glass, and board a tram that slides through a quiet, pressurized tube to an industrial or research district. Everywhere you go, gravity is about 0.38 G. The air feels Earth-like, and the outside world is always just a few meters of rock and a pressure hull away. It's compact, vertical, and obviously engineered. Nothing is accidental. Every corridor, every shaft, every park exists because someone argued for its mass, its power draw, and its role in the life support chain. Then comes the final twist in perspective. Once you do all this, once your city is up and running, you've changed more than Mars. You've changed what humanity looks like to the universe. From orbit, instruments see a hot, organised patch on a cold, chaotic planet. They detect gas ratios over the city that don't match natural chemistry, more oxygen, odd industrial byproducts, stable nighttime light patterns in narrow bands along tunnels and rail lines. To a distant civilization with a good enough telescope, Mars suddenly has a techno-signature, a clear sign that technology is present. That's exactly what we search for when we scan exoplanets: strange gas mixes, unusual heat patterns, artificial light. By building a Martian city, humans end up turning ourselves into the kind of signal we hope to find around other stars. So the city is not just a place to live, it's a proof of concept for off-world civilizations, a template for future colonies, and a beacon saying there is technological life here. From that point on, when someone looks at Mars from deep space, they're not just seeing a red planet, they're seeing us. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.